Hi everyone, welcome to our Conf42 Observability session where we will talk about how we built an observability platform using FluentBit, OpenSearch and Prometheus. My name is Nilushan Costa and I work as an Associate Technical Lead at WSO2 within the Choreo Observability team.
And I'm Isala, and I'm a senior software engineer within Observability.
Before we go into the observability platform, let me first explain why we needed that. Every company nowadays is a software company. For them to serve their customers, they need some sort of software. And this all starts with the developer writing some code and committing it to a code repository. This code needs to come out as an end product to their customers. This could be something like an API, a web application, or a mobile app. There are several different things that the code must go through for that end result to happen. This could be security scans, CI/CD processes, and so on. To do all of that, a platform is required, an internal developer platform. Building an internal developer platform is certainly possible for every company. However, the problem is it takes a lot of time and expertise. We at WSO2 have already built a platform called Choreo, and we are providing it as a service. Now, the important internal developer platform needs several different parts. And observability is one of them. That is because when you run some sort of a program, you need to understand how it is performing. You need to know whether there are any problems within it, whether there are any errors, and so on. And to do that, you need observability. And both of us are in the Choreo observability team, and we built this observability platform within our team for Choreo. And this talk would be about how we created that observability platform. Let's talk a little bit about the history of this observability side of things.
Initially, WSO2 was heavily invested in Asia, and our Choreo platform we were building was heavily centered around Asia as well. And for the observability part, we also use Asia native solutions like Log Analytics, ADX, and Event Hub. So from this simplified architecture diagram, you can see how our initial setup looks like. So we have few services running in our nodes, and each node has Azure OMS agent. And this agent extracts the logs and telemetry from the services, CP and memory, and write them to Azure Log Analytics. And for tracing and matrices, we deploy the OpenTelemetry collector to which all the services publish data and itself publish data to ADX. And we wrote a simple API which queries both Azure and ADX for both login and matrices. And these data then published to our dashboards where we show the logging view and metrics view.
However, there were some challenges after we kept running this for some time. First one was observability doesn't come cheap. Publishing logs, metrics into a cloud platform and querying them costs a lot. So we wanted to try and reduce this cost as much as possible. Furthermore, although we started with Azure in the first place, as time went on, we got requirements from customers to support other cloud providers. Some wanted to have their Choreo data planes, that is a part of the Choreo platform, on AWS, and then there were requirements to run it on Vultr. Then we also wanted to support on-premise deployments as well. So at the end of the day, we had to support multiple different cloud platforms. Also, we wanted to have more control over this observability stack. That is because if we have full control over it, we would be able to build more features on top of it. So these were some challenges that we wanted to address, and in order to do that, we decided to create a new platform using some open source tools.
So with those challenges, we defined our next generation observability stack with two main perspectives in mind. For Choreo users, our primary customers, we wanted to provide speed. That means drastically reduce log latency. And we wanted to also provide smarter tools, such as intuitive UIs where you can see all their services are interacting. And another main key decision we made was we want this platform to be zero instrumentation. That means the user doesn't have to do anything. They just deploy and we take care of the rest. And on the platform side, one of the main concern we had was the cost, right? Because observability is not cheap. we were racking up a lot of infrastructure cost, and we want to see if we can reduce this. And another problem that arose, as Nilushan said, the cloud agnosticity. So we initially, even though we developed this system to run within Asia, there were new prospects coming our way asking, can we run this on AWS? Can we run this on-prem? So we wanted to provide the observability stack for those customers as well. And within EU, especially EU region, this data sovereignty is a really important topic. For example, if a cluster is running on the EU region, UK or within EU, we can't export those data to our central log analytics solution running in US. So we had to run two. So we wanted to make sure we can further scope these logs to the data plane itself. So we comply with this regulation. And another main thing we wanted to do was have control over our logging stack, so we can build and ship features faster since we have full control.
So we decided to create this new platform, and we decided to use OpenSearch, FluentBit, and Prometheus as the main tools for that. FluentBit and Prometheus was used for the log side of things. In Choreo, when users come and deploy their applications, they get deployed within a Kubernetes cluster. So we have FluentBit running as a daemon set, collecting logs from all these containers and publishing them to OpenSearch. OpenSearch was used as a log storage location, and then we used the OpenSearch operator to manage OpenSearch. Finally, we used logging API, that is our own internal API, to do the log fetching part. When a user goes into the Choreo console, the UI, and makes a request to fetch the logs, the request comes through some ingress controllers, API gateways, and then it reaches the logging API, would talk to OpenSearch, fetch the required logs, and send them back to the Choreo console.
Okay, for metrics, we adopted Prometheus, which is a industry standard for metrics. And to manage Prometheus, we use the Prometheus operator because we wanted to send updates to Prometheus and surrounding infrastructure smoothly. And for long-term data retention and high reliability, we use Thanos. And if you're familiar with Prometheus, Prometheus works in a pull model rather than push. As pull targets, we had three. So the first one was cube state metrics, which gathers the Kubernetes context and exports Prometheus. For example, pod labels, pod status, pod allocations, requests, and limits. And those get to Prometheus through cube state metrics. And we had C-Advisor running on all kubelets. C-Advisor is part of the kubelet, standard kubelet distribution, which can be used to scrape the CPU, memory, and other matrices used by the singular container. And we also used a tool called Hubble, which is from Cilium, which is a subproject from Cilium, where we can extract HTTP level, basically layer 7 and layer 3 to 4 matrices without any user instrumentation. For example, through Hubble, we were able to extract all the HTTP status codes, latencies, and save them within Prometheus so we can show how the service is behaving if it's a HTTP service. And everything, all this information is stored in Prometheus. And we have few replicas of Prometheus, which is backed by a Thanos courier, which aggregate this data and serve to our metrics API, which in turn feed the data to our dashboards.
That was like the high-level architecture of the logs and metrics platform, the observability platform. Next, we will do a deep dive into each of these areas, and I will start with the log side of things. Now, our journey with OpenSearch and FluentBit actually started because of a problem that we faced when we were using log analytics. Now, as I mentioned earlier, when our customers come and deploy their applications, they end up as containers within our Kubernetes cluster. So the Azure agent that is collecting these logs would publish them to log analytics, and we were querying log analytics to fetch those logs. However, there was a log latency problem. The time it took for the log entry to be generated by the container and the time that it appeared within log analytics was a little bit too much. As per Azure documentation, this latency could be anywhere between 20 seconds and 3 minutes. And we were also experiencing a latency around that number. So this affected the developer experience in our internal developer platform, because once customers deploy their applications, within our observability view, there was a place where they could look at the logs. So if a log entry is generated and they have to wait a minute or two, that hindered the developer experience a bit. So we wanted to try and improve this by reducing this log latency. During some internal discussions that we had, we decided on a goal. We wanted to bring this latency down to 5 seconds or less. That is because we wanted to give a tail minus F experience when it comes to logs. So someone comes and deploys the application, and once they go into the runtime logs wave, they would see logs coming as soon as they are generated. So we wanted to provide that experience, and we were looking for tools to do that. We evaluated so many tools. We evaluated some other external observability platforms as well. And finally, we decided to go with FluentBit and OpenSearch. The initial deployment of FluentBit and OpenSearch showed a log latency of about 2 to 3 seconds. So that was very good for us. We were able to achieve our goal through that. So we decided to go ahead with that. Now, this deployment was a bit different from the current deployment that we had, because back then we use OpenSearch as a cache. Whenever logs are generated, we pump them into OpenSearch as well as log analytics, and we use two different APIs to fetch data and show them in the UI. We had a live logs API which fetched data from OpenSearch, and a historical logs API which fetched data from log analytics. OpenSearch retained data for about an hour and a half, and log analytics retained for a longer period than that. So since OpenSearch had a lower latency, we were able to show the logs quickly by fetching that data from the live logs API. At the same time, for users who wanted to look at historical data, logs that were about a day or 7 days old, when they set that time range in the runtime logs view, the platform would switch to the historical logs API and fetch them from log analytics. So this initial deployment worked well, and we got a good learning experience with FluentBit and OpenSearch, and we were actually impressed by its performance and ease of use. So therefore, we decided if we are going to build a new platform, we could certainly expand this, that is FluentBit and OpenSearch, to store all the logs. So we created the log stack based on FluentBit and OpenSearch, and we added some other tools as well. So FluentBit was used to collect all the container logs. As I mentioned earlier, it ran as daemon sets. It collected all the logs and published them into OpenSearch. OpenSearch was the log storage location, and all the querying and collecting happened here. When we built this updated observability platform, we deployed OpenSearch as a distributed deployment. Instead of just running it as an all-in-one deployment, we separated out the master nodes and the data nodes and used a distributed deployment. We also used the OpenSearch operator to manage it, and I will explain why in a little while. And then we use OpenSearch dashboards for our internal users. So let's say there is some sort of an incident or a bug that is reported. Then what usually happens is our SRE team needs to access the logs of those services to understand what is happening. With log analytics and Azure, we had the portal to do that, the Azure portal. But with OpenSearch, we decided to go ahead with the dashboard. So our SRE team could log into the OpenSearch dashboard and access these logs. Finally, we kept using the logging API, which is our internal service, to talk to OpenSearch, fetch the logs, and return them back to the Choreo console. Now, when it came to the deployment, we decided to go with a Helm-based approach. What we did was we based our Helm chart on the upstream Helm chart, and we customized it the way that we wanted. So with the OpenSearch operator-based deployment, we had objects like OpenSearch index templates, OpenSearch index state management policies, and so on. So we combined all this into a Helm chart, with the configurations that we wanted. And we wrote it to support different cases where we needed different customizations as well. And the reason why we went with the distributed deployment of OpenSearch was it is better suited to handle production traffic. When we separate out the master nodes and the data nodes, all the cluster management activities are done by the master nodes. And then things like log ingestion, log querying, they are handled by the data nodes. So if there is a burst of logs, if there is a high amount of traffic for querying, all that would go into the data nodes and nothing would happen to the master nodes. They could continue managing the cluster. So by separating this, we were able to achieve better availability and not affect different functionalities because of something like a spike in logs. Also, one of the main reasons why we went with the operator was it made upgrades much easier. So when it comes to OpenSearch, if you want to do a version upgrade, there is a particular order where you need to upgrade the nodes. If we wanted to do that with multiple Kubernetes clusters, that would require a lot of manual intervention. Because the thing is, with Choreo, we have this thing called private data planes, where we set up private Choreo data planes for customers, and those are dedicated for that customer itself. So when we get a lot of customers, that means we will have to manage upgrades in each of these data planes. So doing things manually was error prone, and then it would take a lot of time as well. But with the operator, it made the upgrade process much easier. We could specify the new version, and the operator would handle the restart order and everything. Furthermore, when it comes to managing the cluster in day-to-day running scenarios as well, operator takes care of things like rollout restarts, then other index management, and so on. So we went with the operator. And to ensure that there is backups, we implemented backups at several levels. The first layer would be backups within the OpenSearch cluster. In order to do that, we went with primary shards and replica shards in OpenSearch. So what happens is, when a log entry is ingested into OpenSearch, there would be one primary copy and one or more replica copies. Thereafter, we spread all these shards into different OpenSearch nodes. And then these nodes were spread across different failure domains, something like availability zones. As an example, let's say there is an OpenSearch setup where we have one primary shard, two replica shards, and three OpenSearch data pods. What happens is, one OpenSearch pod would store the primary shard, and the other two pods, they would store the replica shards. And these three pods would be spread across three different availability zones. The advantage of that is, if one of the pods go down, or even the PVC that is having the logs, storing the logs, gets deleted, once a new pod comes up, it would be able to replicate data from the other OpenSearch pods. That happens within OpenSearch internally without any intervention. And by having failure domains like availability zones, even if an entire availability zone goes down, the observability stack could continue working. Log ingestion and querying could continue with the remaining pods. So that was like the first layer of backup. Then we also enabled OpenSearch snapshots because we could use that as the last resort. Let's say we have all these pods spread across different availability zones, but then due to some disaster, we lose everything. In that case, we are able to restore logs from the snapshot. And the snapshot would store logs in a different location than the OpenSearch cluster. By running this platform, we were able to achieve a lot of cost saving as well. Instead of using log analytics and in switching to FluentBit and OpenSearch, we were able to save about $1,800 per month, the log analytics ingestion and storage cost. And then there was one particular customer on AWS where they were able to save about $2,500 USD per day from their AWS infrastructure cost. Now, there was one incident where the workloads that were deployed by this customer started printing some error logs, and all that was ingested into AWS CloudWatch logs. And when they started querying the logs, this added up querying cost as well. And that's why their infrastructure bill skyrocketed. And by moving to a platform like OpenSearch, there is no extra querying cost. There is some cost for storage, but the querying cost would not be there. That's why we were able to save such a lot by using a platform like this. So there were several lessons that we learned during this time. When it comes to a platform where you have containers publishing different types of logs, it's better to store the logs in the raw format that they get generated. And if someone wants to show it in different formats, they could use different internal services to break it up into different formats. And then log throttling is something that is useful. When FluentBit starts publishing logs to OpenSearch, there could be cases where the OpenSearch cluster could be overwhelmed. To prevent something like that from happening, we could use log throttling, and we were able to do that by writing a custom Lua script and adding it to FluentBit. Health monitoring is also important in a platform like this. To do health monitoring, we used an external tool to check the health of OpenSearch, FluentBit, and our logging API. And health monitoring has to be done at different levels. You need to see whether all the pods are up and running, whether the CPU usage and the memory usage of them are all right, whether the disk is reaching its capacity, so on. So all that needs to be monitored. And the storage medium that is used for OpenSearch plays an important role as well. There was one deployment that we did with EFS in AWS, and we noticed that it didn't have the performance that we expected. Thereafter, we switched to EBS and things started working properly afterwards. So the storage medium plays an important role. Also, when you have an observability stack like this, you need to look at everything as a whole when you're debugging. So there could be cases where FluentBit pods would not be able to publish logs. However, the underlying cause could be something to do with the storage medium that is used in OpenSearch. So simply by looking at the metrics of FluentBit, you can't determine whether you need to increase those metrics because of a usage increase or whether there's an underlying problem elsewhere. So that's why you need to look at everything as a whole. And then when it comes to FluentBit configurations, there are so many configurations. And if you don't configure them properly, log ingestion could be affected. So sometime back, we were using the iNotify watcher in the FluentBit tail plugin, and there was a problem where it stopped collecting logs after some time. And by switching to the file stat watcher, we were able to fix that problem. So you need to know the configurations that you're using in these stacks if you want to make it run in a smooth manner. And what on screen right now is a screenshot of the runtime logs API. Here we are showing logs of the application, that is the workloads deployed by the customers, and the gateway, and we are able to do different types of filtering on that log. They are able to query using different strings, and all that is powered using the observability stack we built using FluentBit and OpenSearch.
Okay, now let's switch to metric side of our observability. So for metrics, we had 3 high-level goals to provide to our users. One is provide HTTP metrics, a clear insight into request rates, error rates, latencies on their services. And the second is usage metrics. We wanted to show to our customers how much resources were allocated to them, how much their CPU and memory are used from those allocated cost usage. And another very exciting goal we had was to provide a service diagram. So this is automatically generated visualization of their services, how they interact with each other without doing any user intervention. A key enabler of this HTTP metrics, and especially the Zero-Instrumentation and this beautiful diagram I will show in a later slide, is Hubble, which leverage Cilium and eBPF. On the diagram on the left, you can see how a traditional service mesh, particularly like Istio something, would work. So every request that comes to the particular application goes through a proxy within the container node pod itself, right? So that comes to the pod, and then the request get proxied to the backend. And during this proxying process, we can extract telemetry like error rates and whatnot. And on the right, you can see the eBPF powered solution Cilium team has made. So in here, you can see when a request comes, it goes to when request is directed at a backend, it first directly goes to a envoy proxy, which is residing within that node of the designation pod. And within this particular envoy instance, they extract the telemetry data, and then they again with eBPF that request to the correct backend. This get rid of lot of the overhead that will be required to run a service mesh at this scale to provide zero instrumentation. And through envoy, we are able to extract red matrices like error rates, HTTP duration, high HTTP duration for HTTP. And for other layer 2-3 protocols, we directly use the data extracted through eBPF. And so talking about that's the HTTP part, and talking about the CPU and memory usage and file system and network usages, for that we use a solution called cAdvisor, which is a standard component integrated to every kubelet on each node. So this cAdvisor subprocess talk to the container runtime running within the node and build up a cache of what are the containers running within that. And then it interacts with the C groups file system of that particular container. And from those C groups, they read the values for CPU, memory, and other matrices that need to be extracted. And after reading those values, cAdvisor exposes a matrix endpoint, which the Prometheus instance can scrape. So with this, we can get detailed resource usage for every container out of the box. So to enrich our metrics with kube context for particularly labels and annotations, we use another solution called kube state metrics, which establish a connection with the kube API and provide a real-time up-to-date snapshot of the kube state. So this also exposes a HTTP metrics endpoint, which Prometheus can come and read. And these data get into Prometheus, and we correlate with other information like, so for example, from the cAdvisor, we can see the pod name, and we correlate that with the labels extracted through this. So users can query the CPU usage by a label. For each production gate metric systems, a reliability and scalability as well as long-term data retention is a key requirement. For this, we use Thanos. So Thanos is able to integrate with lots of existing blob storage solutions like S3, Google Cloud Storage, and Azure Blob. And also Thanos provides a load balancing capability for Prometheus to run in a HA mode. If you look at this diagram, this is a high-level architecture view of how Thanos run. I won't go through each and everything, but I just wanted to highlight this diagram. So on the bottom of the screen, you can see the external Prometheus server as well as the Thanos sidecar. So these two run in a single pod, and the Prometheus server talks to all the Prometheus endpoints and extract the data and write to the disk, right? And this particular disk, this file Prometheus create, and the Thanos sidecar has a subcomponent called shipper, which read these files and ship it to a blob storage we configured. So this provides the long-term retention. And for load balancing, Thanos also exposes a new API called Store API, which is exposed through all the Thanos endpoints. And when we deploy the Thanos Courier component, as you can see in the top of the diagram, it also have a Store API which connects to the Store API running within the sidecar and is able to extract data. So when we run a single query on a Thanos Courier, it distributed that query for both or like how many instances they run and aggregate the results and give us a single point to get the state of the cluster. And there are other things like Thanos Query Frontend for response caching. We are not currently using those. But what we do use is the Store Gateway. So Store Gateway allows us to again query the data that was stored within the object storage. So this is another component and which get plugged into Thanos Courier via the Store API. And when we query for data that is not available within the Thanos instances running, it automatically goes to the store gateway and it reads the data off of the blob storage and give us the result. So this gives us a clean way to inference metrics. And yeah, it's good. And all of these complexity translate to these beautiful design views, right? So in here you can see the request per minute, total success, total failed, as well as latencies and other key metrics. For example, you can see the memory usage and CPU usage as well. Not just the usage, we can see the limit and the request as well. And all these data are provided by Thanos and Prometheus in a near real-time manner. So users can easily understand when there's a spike happening or if their service is slowing down, what's going on. And another key feature here is when you see a spike and click on the particular, we call the logging API to gather the related logs. This provides a easy and scalable way for users to debug in production. Okay, so this is the diagram I was talking about, the service diagram. This is a dynamically generated UI which shows how each of your components interact with each other. And from here you can see how the error rates, latencies occurs between two components. These are like isolated components. And particularly, for example, if one service is failing, we can easily use this diagram to identify the root causes of the problem. And so this is all powered through zero-instrumentation metrics approach. Okay, so there were a lot of things we learned the hard way while developing this system. So one of the key issues we were facing as soon as we started developing this system was the request count, basically request rate, isn't accurate. So if we send 15 requests, the diagram may show 13.8 or something. So our older system that chooses open telemetry and event-based metrics was showing the exact count. We were wondering what is the reason for this, and we came across like few documentation from Prometheus saying if you're using Prometheus, you can only see the summarized and aggregated data. So if you want exact counts and events, especially for, let's say, for billing purposes, you can't use matrices. So for that, you need to use logs. And once we understood that, everything clicks. And another thing we learned while developing was, even Nilushan told, using an operator. If there's an operator, use the operator. Because the Kubernetes operators reduce the complexity of managing stateful sets and the underlying infrastructure for that very easy. Otherwise, when we are doing upgrades, it's a multi-day planning step. Right now, what we are doing is we just bump the Helm chart and the operator takes care of the rest. And another issue while we actually faced during our initial production deployment was /metrics API can screw up the whole thing. The reason for this was, so as I mentioned, we use Hubble to collect per pod metrics data. And there was a bug in the Hubble's metrics endpoint where sometimes the pod information is not cleared from the metrics. So that means like if the pod get deleted, that metrics information lives forever. This is particularly challenging when we have a cluster that's running a lot of cron jobs, which creates tons of pod each minute. And turns out this is a issue with Cilium's pod management cycle, and they had fixed it in a later version. So once we bump to that newer version, everything resolved. And another issue we ran in the early days of our development of this platform was we often see the file corruptions. So when you are querying in Prometheus, if there's a like single block was corrupted and we are querying for a longer range, the whole query fails saying this file is unreadable. And while again browsing the documentation, we noticed like Prometheus explicitly mentioned not to use NFS. So we were using EFS, AWS NFS solution. And since we found that, we moved to block storage, and all the platforms, and we didn't have any issues since then. And another issue we are currently facing is the sum of rates on rate of sums. So when Prometheus has a lot of aggregation functions, especially rate and sum, and the order of the operations we use matters significantly. So we had a recording rule that aggregates some data and put the sum in our data storage. And when we are taking the rate of that particular time series, we notice some errors. So while investigating only, we notice this particular issue. So let's revise the cost, because we did a lot of things, right? So previously we spent around close to $1,200 on ADX and $1,000 on log analytics per month per data plane to retain this data and serve this to our customers and for ourselves as well. But with our newer open source stack, we only pay for compute and storage. So since we manage everything, for compute, we use around 250 USDs, and for storage, it's around 100 USDs. So this roughly translates to around 70% overall cost savings. And as well as this gives us more flexibility and more control and better performance.
So that brings us to the end of our deep dive sections. And next, we'll go through some summary points about what we learned when building this platform. When it comes to cloud providers, providers like Azure, AWS, they have very good support when it comes to observability. They have powerful querying languages, easy to integrate solutions when you want to get observability data from something like a Kubernetes cluster into Azure. So all this work really well. But the thing is, when you want to work with multiple cloud providers, you will have to go through some overhead to do that. That is because different cloud providers have different querying languages, different APIs, different deployment mechanisms. So if you want to use these cloud providers' native solutions and support multiple vendors, you will have to add support for each and every cloud provider. But if you use a common platform where you use a common set of services everywhere, it would be very easy to enable observability for different cloud providers. And the other thing is, when you have a stack that you have full control over, it would be very easy to add additional features. So we recently introduced an alerting feature within Choreo, and we built that alerting feature using the stack that we created. It is powered using Prometheus, FluentBake, and OpenSearch. And debugging also becomes easier when you have the same setup everywhere. Let's say you have different cloud providers and different APIs to connect to each of them. If there is a problem, you need to figure out where it went wrong. You need to understand about that API and the way it's deployed and so on. But if it's the same setup, debugging would be similar everywhere. So debugging becomes easier. And cost would also reduce when you use a platform like this, an open source platform that you build. So cost could also be reduced by doing something like that. And that brings us to today's session on how we built this observability platform using some popular tools. Thank you all for joining with us for this session, and hope you were able to learn something from it. Thank you.
Thank you all.